Finish out chapter 6 today. And chapter 7 has a lot of the same sort of topics. So what I really want to hit on chapter 7 is some of the reactions that we haven't dealt with before, specifically redox reactions or oxidation reduction reactions. And then I think I'm going to skip chapter 8 entirely on the gas laws, because that is pretty straightforward. And I really want to get into thermochemistry in the last bit of time we have, just to hit a couple of the really important things. So for the folks who are going on to take 220, thermochemistry is going to be really, really important. So I want to sort of introduce that before we call it a term. So if there are any questions or concerns about that, like, oh my God, I really wanted to learn about gases, we can quickly hit on gases, but really it's a fairly straightforward chapter. How straightforward? There's basically one equation you need to know. That's it. So we can spend a short time on it, but I think it's really more important to get to the thermochemistry. So we're going to basically finish up with stoichiometry. Of course, you never really finish with stoichiometry. It's there lurking behind corners at all times. But the recitation this week that my groups will be doing this afternoon will be dealing with just finishing stoichiometry and sort of an introduction to redox reactions. We may not get to redox today, but we definitely will on Thursday. So one of the things that I noticed about the test is a lot of people are still having problems with stoichiometry. And I think one of the things is people are making assumptions that reactions are always balanced, that there's always an equal amount of reactants going into products. That is true when you have completely balanced sets of reactants and products. That isn't the case if you have something that's in excess and you have something that's limiting. So I sort of want to revisit those today. There was also a question on titrations, which is basically solution stoichiometry. So sort of, and there was a number of people who had issues with that one as well. So I want to talk about that somewhat. So what you need to remember about solution chemistry is you need to take the additional step as it's mentioned here, because we always deal with moles. Though I still had some people balancing grams of when you had a balanced reaction, thinking that 2 to 1 in a balanced reaction means 2 grams to 1, and I sort of I'm hitting my head saying no, that's not it. The helpful thing about solution chemistry that I think even makes it easier than regular sort of chemistry is that in general you do not have to figure out the number of moles based on the molar mass of reactants or products. Why? Because basically that information is given to you already, because you have a volume of a reactant and a concentration of a reactant. And as we know, if you multiply the concentration, which is in moles divided by liters, and you multiply that by liters, your volume, boom, you got moles. So you don't really have to go, looking up how much is a mole of phosphoric acid or sodium sulfate. You don't have to look all that stuff up. It's right there in the concentration and the volume. So then once you've done that, balance the equation. You always have to do that. That's always essential. And then it's just a simple matter of balancing moles on one side and moles to the other. And then if you're asked, look at what the question is. Is the question asking you what is the concentration of products, or what is the volume of products that are made? Just look and see what units are required. And as I keep harping on about, it's really, really important to keep the units at all your calculations. On the test, I saw a lot of people dividing things like molarity, and then dividing that by liters, and then coming out with some weird sort of, moles per liter squared kind of stuff. It's like, don't don't do that. Always multiply and keep your units where either in the numerator or in the denominator, because you make a lot of mistakes when you don't do that. So here's our strategy doing any of this stuff. We know that when we first started doing stoichiometry, we'd be given like grams of reactants, and we'd have to convert grams of reactants into moles. In solutions, you're given volumes and a concentration. We turn that into moles, and then always balance our moles of reactants, moles of products. One thing you really need to make sure of: do not assume that, the question on limiting reactants in the test, I didn't tell you it was a limiting reactant problem. So some people just assumed it was not a limiting reactant problem. Always, when you're given units when you have two reactants, always make sure that find out which one of them is limiting. So if you have A and B going to C and D, and you're just given some amount of A and some amount of B, you can't just assume that those things are balanced perfectly, because that rarely happens. So you need to figure out, how many moles of A do I have? How many moles of B do I have? And which one of those will limit my amount of products? Don't assume that I can just pick one of them. I can pick either A and that's going to make a maximum amount of C and D, or pick B and that's going to make a maximum amount of product, because that's not always the case, okay? So let's do a question like that now. So here is a classic sort of reaction, actually a reaction that takes place. Some of you probably did this reaction after Thanksgiving dinner. Because in your stomach, you have, like I mentioned before, it makes hydrochloric acid, which may seem bizarre, but it's true. And the concentration of it is around 1/10 molar. So pretty concentrated. That gives you a pH of around 1, right? So it's, if you have an upset stomach, you will take something, an antacid, for instance. There's lots of different kinds, but all of them are going to be bases of some kind to neutralize this acid. So that is basically a titration, right? Because what you're doing is you're calculating the amount of acid on one side and figuring out how much base that is going to take to balance it out. So basically you want to balance the number of moles of acid and moles of base, or H plus and OH minus. Later on, as you go into more advanced chemistry, you'll find that there's a lot of other more complex acids and bases that don't have H plus and OH minus. But for right now, we'll sort of basically work on these. So the question is, you take a tablet of magnesium hydroxide. So it's magnesium hydroxide. Is that going to be an acid or a base? Don't all yell out at once. Base, right. All about that base. So what do we do once we figure out we got if we're acid and our base? We need to write a balanced equation. That's super important. And convert this mass, so this tablet containing this amount of magnesium hydroxide. We need to figure out how much magnesium hydroxide is that. Go to our balanced equation and figure out how many moles of H plus that would react with. So let's do that. So here's our question. So we have, in your stomach, we have about 10th molar HCl. We've taken a 100 milligram tablet of magnesium hydroxide. So what is my reaction? What's the reaction that takes place here? Basically, what are my two reactants? Right, fair. So my first reactant is the HCl, right? So I've got HCl plus, and my second one is magnesium hydroxide. Now this is important that I get, what charge is magnesium? What's the charge on magnesium as an ion? +2, right? It's always +2 because it's in group dose. So when it forms an ionic compound with magnesium hydroxide, there's two hydroxides there. So they come together and make what? What are my two products? Maolan's got one product is water. That is correct because we have H and OH make water. And what's my other product?
Magnesium dichloride.
Do we call it magnesium dichloride?
Oh, it's a metal. Magnesium chloride.
Magnesium chloride, right. I mean, you're absolutely right. There's two chlorines, but it's an ionic compound, and magnesium is always +1. So the only formula for magnesium chloride is MgCl2. It can't be anything else. It's not a transition metal, so it can't be MgCl sometimes and MgCl3 sometimes. That's not the case. Right, so this is our reaction. Is it balanced?
No.
No. So how do we balance this?
You can start by adding another 2 to the HCl.
Right, so we're gonna need two chlorines because we got two chlorines as products, so we need two chlorines as reactants. That is true. And so what else do I need to balance? Right, two waters. Because I've got two protons are going to be coming from here, and I'm going to get two hydroxides coming from there. And so when they come together and neutralize each other, they're going to form two waters. So that is my balanced equation. So 2 moles of HCl are going to come together with 1 mole of magnesium hydroxide and make 2 moles of water and a mole of magnesium chloride. So what's the next thing I have to do? So that's step 1. What's step 2?
convert grams to moles.
Right. I've got, basically the question is how much acid will be neutralized by that amount of magnesium hydroxide? And we know reactions occur mole to mole, not gram to gram. And so that's how big the tablet was. I need to convert that to moles. So 0.10 grams times 1 mole over how many grams? So anyone look that up for me real quick?
I think it would be 58.33.
Okay, I'll take your word for it. That was one of the things on the test you can use the internet for. I do not care. If you calculate the molecular mass of magnesium hydroxide or you just look it up, I personally just look it up. So it saves you a lot of time, and it keeps you from making silly numerical mistakes. So so that cancels out grams. I'm left with moles. How many moles of magnesium hydroxide do I have?
I believe 1.7 times 10 raised to the negative third power. Unless I did that wrong.
Actually, go ahead and this is another thing. Use more digits here than you need. Yes, I realize that our final answer is going to be 2 significant digits because we have 2 significant digits in the mass, 2 significant digits in the concentration. But you do not want to limit your accuracy or precision by limiting the number of digits too early. So what's my answer here? You can give me like 3 or 4 significant digits.
Instead, I believe it would be 0.0017.
0.00. It's still only 2 significant digits. Give me 3 or 4.
Okay, let me calculate that real quick.
0.001714.
714. There we go. So that's how many moles of magnesium hydroxide I have. So how many moles of HCl will that react with?
2, right?
Right. So we need to multiply that number by 2. So we just go, I have moles of hydroxide. So I want to take my moles of hydroxide and multiply that by the ratio of HCl and magnesium hydroxide. So it's 2 HCl for every 1. So how many moles of HCl is that?
Like 0.1428 if you don't put it into scientific notation.
Yeah, I'd sort of avoid the scientific notation till the end.
Right.
I have trouble punching that into a calculator. So how many moles of HCl is that?
0.01428.
Wait a minute, really?
If you multiply 0.001714 times 2, that's
Should be
what I-
0.0034, shouldn't it?
I guess
3428?
yeah, sorry.
Okay. So that's how many moles of HCl we have. Now, we need to figure out what volume of stomach acid contains that many moles of HCl. So again, I urge you, I beg you, I plead to multiply these things out. So I've got 0.003428 moles of HCl multiplied. What am I going to multiply that to get me liters of HCl. I want to end up with liters. So what do I put here so that I get liters out at the end? Because that's what I'm looking for. I'm looking for a volume.
The molarity.
Right, I'm going to plug molarity in there. How?
0.10 moles per liter.
How do I do that? Where do I put each one?
You put liters on top and moles on the bottom.
Yes, exactly. That's the important thing. That's the problem I saw a lot of people have on the test. They know they got moles and they got a concentration and they got to get volume at the end. So they're just going to, okay, I'm just going to divide. Divide what? I mean, you need to get it's really important to get your units right. And so, because as I saw before, you're going to end up with these bizarre units of like, moles divided by liters squared, or moles squared over liters cubed, and all this bizarre things. To avoid that, always multiply. So 0.01 molar HCl means in 1 liter, I have 0.01 moles. That's what that means. That's the literal definition of that. So now I can cancel moles and I'm left with liters, which is what I want. So this system will always, if you get the unit you want at the end, you've probably set up everything. And if you do this on the test and then make some, brain fart mistake, like, I have a little bit of dyslexia. I do this all the time. I take my 3428 and I'm punching it into my calculators 2834 because I do that all the time. I'm not going to ding you that much for it because I see you can set this up. You know what you're doing. Your brain just didn't work there for a minute, and that happens to everybody. So you'll get 3/4 of the mark, if not more, for setting it up properly. So how many liters is that? How many liters of HCl is that?
0.03428.
0.03428 liters. Now I go back and see how many significant digits I have. This is why it's important to carry over as many digits as possible. If we round too early, we lose, excuse me, we lose some of that precision. How many significant digits do I want to report? Because if I report this number, I'm going to make a nasty comment on your paper. What should you report? What should the final answer be?
There should be 3 sig figs, so it should be 0.
3? Why 3?
Oh, sorry, the leading 0, it doesn't count.
That's right.
2 sig figs.
2, right? Because there's 2 here, and there's 2 here. So there's 2 in the concentration, and there's 2 in the mass. So what's my final answer?
0.034 liters.
Yeah. And if you wanted to put it in milliliters, what would it be? 1, 2, 3.
34 milliliters.
Yeah, 34. Either one is a volume, so that's fine. So and then of course you get the answer of someone who rounded too early. All right. So I'm just going to go through. Oh, go ahead.
Could we quickly go back to the where the actual problem was? I just wanted to take a quick screenshot of it.
Oh, sure.
Thank you.
Although this should be, I think I posted this. So you should have them. So
gotcha.
this, you want the question, this question?
Yeah, the question.
Okay,
Exactly.
there you go.
Thank you.
All right, no problem. Although, yeah, I think these slides are all in PDF form. You can look at all of them.
Thanks.
No problem. So let's just really quickly look at this because I really want to get going. So you know that mercury is a problem. There was like it's toxic, and one of the things about mercury is that it tends to accumulate. In other words, little critters take up mercury, and then they're eaten by bigger critters and eaten by bigger critters, and so the mercury tends to increase in concentration as you go up the food chain. So you want to get rid of mercury at the source. And one of the things you can do is react it with sodium sulfide and get mercury sulfide forming that basically takes it out of the water. And so when you're doing a reaction like this, when you have a concentration and a volume of one item and a concentration and a volume of a second item, what do you do with that information? Well, got to have a balanced chemical reaction. That goes without saying. Figure out which one of those will create less product. So the product you're looking for is mercury dose sulfide. So I've got mercury 2 nitrate, that's mercury 2 nitrate there. And my other reactant is sodium sulfide. Now remember that sulfide, like oxide, is a -2 charge. So that's Na2S. And my reaction is going to be the formation of mercury 2 sulfide. So this is mercury 2 sulfide down there, HgS. Mercury with a +2 charge, sulfide with a -2 charge, 1-to-1 ratio. So how do you figure out which one is limiting? How would you do that? What would be your game plan for this sort of problem? So if you had that in a test, what would be the first thing you would do? Yeah, lay out the reaction. Figure out what the reaction is going to be. So let's do that super quick. So I have 2 reactants here. So I've got my mercury nitrate and I've got my sodium sulfide. Well, I almost made a mistake there. So what is going to be the ratio of those 2 things to make the product HgS? So if I add, this is my reactant A, my reactant B. I add them, so those are my 2 reactants. What's going to be the ratio between them?
Is it going to be 1-to-1?
Yeah, 1-to-1. Yeah, very good. Yeah, because 1 mole I have 1 mole of mercury on that side with that reactant, and I have 1 mole of sulfide on that reactant. They come together in a 1-to-1 ratio, so it's just 1-to-1, which is nice because then the other thing you notice is that there's 2 moles of sodium and there's 2 moles of nitrate ion. Those balance as well. And so my other product will be 2 moles of sodium nitrate. But we don't really care about that, because what are these ions? Because that's an ionic compound. What do we call those?
Spectator ions?
Right, because this is going to be in water. So I'm not actually going to make this. That's not actually going to form. What I'm going to get is 2 moles of sodium ions and 2 moles of nitrate ions. I had them at the beginning, and I'm going to have them at the end. So they're not really involved. So my net ionic equation is Hg2 plus sulfide 2 minus make HgS. That's it. So basically all you would have to do in this situation is figure out how many moles of mercury do I have here? In other words, how many moles of mercury nitrate do I have? Figure that out. That will tell you the number of moles of product, because it's a 1-to-1. Same thing here. Figure out how many moles of sulfide ion you have based on your concentration. That will give you the number of moles of mercury sulfide. Whichever one is smaller, that's how much product you're going to get, okay? And if you want to see if you want to do that and figure out what the answer will be, the answer is 0.47 grams. So if you want to run through that and check your answer, it's 0.47 grams. Okay. Now, let's move on a little bit with dealing with solutions. One of the most common things you're going to do in a lab is taking concentrated solutions. What do I mean by a concentrated solution? What does that mean? What's the difference in a concentrated solution and a dilute solution?
A dilute solution, I'm pretty sure contains water.
They both contain water. Any aqueous solution's got water in it. But what's the difference?
The amount of solute dissolved.
Bingo. Yeah. So which one? So a concentrated solution has more solute dissolved in it. And so if a lot of times we call something that's concentrated, we call this a stock solution. Why? Because in the lab, we'll use a dilute solution of something all the time. Like for instance, that hydrochloric acid under the in a safe environment in a cabinet, strictly for acids. You don't keep acids and bases together. That's a bad idea. You'd have all your different acids. You'd have hydrochloric acid and sulfuric acid and nitric acid and acetic acid, and all the things that you need to do different reactions. But you'd have them there in a very, very concentrated form. Why? Because you're going to be using lots and lots and lots of the dilute stuff. And it's a pain to have a 400 liter jug of dilute acid all the time. It takes up a lot of space. And you don't need that much of it at any one time. So what you do is you go to a stock solution, which is concentrated, and you take a little bit of it out, like say you take like 10 mils of it, and you dilute it to a liter that you're actually going to use. So here you just add solvent, in most cases water, and now I have what I call a working solution. Like when you're doing your titrations, you don't use like a 12 molar solution of HCl for a lot of reasons. One, because the volume required for it would be so incredibly low, it's really hard to measure. And two, 12 molar a hydrochloric acid. It's really dangerous stuff, and you don't want to, be using that if you don't have to. If you spill a little, 0.1 molar HCl on your skin, you can just wipe it off. If you spill 12 molar HCl on your hand, it's going to be a much bigger deal than just wiping it off. You're going to have to rinse that underwater for a good long time and put some, baking soda on it to neutralize it and all kinds of things. So we generally use dilute solutions a lot more frequently than we use concentrated solutions. So when I take my concentrated solution, I need to quickly convert the concentration of my stock solution to the concentration of my new working solution. So I do dilution, just adding solvent to make a more dilute solution or working solution. Now, this is the important thing to remember. Only the volume changes. That's it. The amount of working stuff in that solution remains exactly the same. So in other words, the moles from my concentrated solution are going to equal the number of moles in my dilute solution. That does not change because it's determined by how much of the concentrated solution I started with. If I started with, let's say, 100 milliliters of a 10 molar solution of HCl, that is 1 mole, right? That's 1 mole of HCl because I have a 10 molar solution and I took 1/10 of a mole, 1/10 of a liter, multiply them together, you get 1 mole. So whatever I dilute that to, it doesn't matter. I still have 1 mole of HCl. If I dilute it to 10 liters, if I dilute it to 1,000 liters or 1,000,000 liters, my amount of my solute remains the same. And so we know that how do we calculate moles? Well, it's volume times concentration. We've been dealing with that forever, right? This is in, this is in liters, and this is in moles per liter. That is why chemists always use molarity. Well, not always, but like 99% of the time, we use molarity because that way we can figure out moles exceedingly fast. Just boom, we just multiply volume by concentration and we're done because that will give you moles, okay? And so I think most of you probably know this already, but all we need to do to figure out either the new concentration or the new volume is to just take my initial volume and the initial concentration, because that's moles, and multiply that by the second volume and the second concentration, because that's moles too. So basically, as the volume goes up, the concentration goes down in exactly the same way. So if my volume goes up 10 times, my concentration goes down 10 times. If my volume goes up 100 times, my concentration goes down 100 times. And the way to think about it is just moles, the number of moles I start with has to equal the number of moles I finish with. And you can see that here. I mean, this is it's really easy to see when you have colored solutions. So copper has this really pretty, copper 2+, has this really pretty sort of green, blue, aqua color. And when you dilute it, you can see that it goes from being a darker color to a lighter color. And we can actually use this later on when we get back together in the lab. We can use this difference in intensity to actually figure out the concentration, because what we can do is shine a light through this, and the amount of light that's absorbed by the solution is a direct indicator of its concentration. And the funny thing about that is so we read the absorbance at a particular wavelength, and that is going to equal some constant times the concentration. And this is called Beer's law. I just love that it's called Beer's law by some guy named Beers. Doesn't have anything to do with beer. So this is a really common experiment that you will be doing, hopefully, when we all get back together again. It's kind of tough to send a laser to everyone's house to do this experiment. But
Professor?
yeah.
So could you use Beer's law, like the experiment, to kind of determine the concentration in any substance for anything?
If it absorbs light, yes. If it absorbs light. So in this instance, this absorbs visible light. So we could just basically shine a light bulb and just look at white light. But a lot of things are colorless, but they will absorb either in the infrared, will absorb infrared light or UV light. And so basically what you do is you just scan a whole series of wavelengths and see which ones get absorbed by your molecule of interest. And then you use that. In fact, that is one of the experiments that's in your online lab manual. It's one of the experiments we would be doing if we were in the lab right now. You basically look at the wavelength and check the absorbance and see, so you get something that looks like this. So those would be all the different absorbances at different wavelengths. And so what you would do is say, which one gives me the highest absorbance? Right there. And come down. And then I would use that wavelength to see, because the highest absorbance gives you the most sensitive detection. And so we would set our wavelength to that, and then we would go ahead and measure a whole bunch of absorbances and then plot them against concentration. So yeah, it's a classic experiment. And it's something that we do in the lab all the time to measure concentrations. So dilution, just like we were saying a minute ago, N is equal to the number of moles. M is my concentration in molarity, and L is the volume in liters. And so the number of moles before and after are going to be the same, because I've just taken, like in the last example, I've just taken some copper, copper sulfate or nitrate, whatever it was. And I've taken it from a concentrated solution, and then I poured it into a new container with some water. The water didn't have any copper in it. I've added the copper myself. I've added a specific amount of volume, which is a specific amount of moles. So the number of moles is the same. So my old concentration times the old volume is going to equal a new concentration times the new volume. That makes it really, really easy to calculate. So you either use this. So this is the usual equation we use down here. So my initial concentration times the volume. And the thing to remember, the only mistake that I see students making with this is that they will switch the two volumes. They'll take the initial volume of the initial concentration and multiply it by the final volume, and then come up with something weird. But if you just remember, sort of keep it stuck in your mind, moles equal moles. The only way for moles to equal moles is for my initial concentration and my initial volume equal my second concentration and my second volume. It has to be that way. Don't switch them around, because moles equal moles. All right, let's do this one real quick. So I have, anyone know what this is? Curious. You remember what the OH group is? Just curious. That's an
Kind of-
alcohol group.
Oh.
Methanol, exactly. So basically it's methane. So if you have a single carbon, it's methane. And then you have ethane and propane and butane and pentane and so on and so on. And so if you have an OH group, that's an alcohol group. And so you would call it methanol, ethanol, butanol, so on and so on. So yeah, so this is methanol, which you do not want to drink. And I have 25 mils of a 2.04 molar solution. And then I dilute it to 500 mils. So what is the new concentration? So go ahead, work on that for a couple minutes and see who gets it first. Just use our good old C1V1 equals C2 V2. And the question is, what is C2? What is the second concentration, the new concentration?
Professor, if they're both in milliliters, do we have to still switch to liters?
That's the question, right? I mean,
Okay.
you should, you should, but you don't have to, is the answer. You should, but you don't have to really.
Okay.
Because you see that basically you're going to be switching milliliters to liters and then right back again. So you don't really have to, but you should, just to be on the safe side. And Ryan, oh, no. Mawelan got there first. Yes, 0.102 molar. Yeah, and just a simple matter, I was taking 0.25 liters times 2.04, and that equals X times 500 liters. Divide both sides by 0.500 liters and you solve for X. Yeah, there you go. .102, excellent. So here's some other units. I had some questions before the last test because on the chapter 6 deals with some of these new solution concentrations that we haven't gotten to. And these are what we're doing here. So they weren't on the test. We're going to talk about them now. Now, 99.9% of the time, molarity is going to be the unit you're going to get because we're chemists, people. We deal with moles. We want to know, we're doing reactions, right? We're doing reactions. I'm going to be adding a solution of A and a solution of B. I need to know how many moles of A and B I have, so when they come together, I know how many moles of product I'm going to get, and blah, 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 blah. So when I'm doing reactions, molarity is essential. I have to know what the molarity is. What if I'm not doing a reaction? What if I need a solution of stuff to do something else? Well, there are other units of concentration that are used really frequently. Not as frequently as molarity, but pretty frequently for other applications. What are those other concentrations? Well, mass percent, and we've dealt with figuring out mass percent. That is just taking how much solute do I have in a particular volume, figuring out what the mass is, and then just dividing that by the mass of the solution. Now, the mass of the solution is both, remember, that was actually a question on the exam about this. The mass of the solute what's dissolved in the solution, plus the mass of the solvent. So you need the total mass on the bottom. A lot of people got tripped up on that. They just had the mass of the solvent on the bottom and the mass of the solute on top. You want the total mass, because that's what percent is, a fraction of the total. Another one we use is parts per million and parts per billion. So either ppm or ppb. We use those for like really dilute solutions that are so dilute that if we were to give like a concentration, there would just be a whole bunch of zeros. Like it would be 0.00000, 17 molar or something. Well, it's kind of a pain to write all those zeros, or to put it in terms of, 1 times 10 to the 1, 2, 3, 4, 5, 6 minus 6. It's a lot easier in those situations to just have a whole number, and that would be parts per million. In other words, what's the mass? And again, it's just mass percent again, but instead of out of 100, it's out of 1,000,000. So I just take the mass of the solute, and in like things like lead in drinking water, is because the concentrations of lead are so low, and lead is so dangerous, that it's important that you, even in parts per billion, it's important to know it's there, because even that can cause toxic reactions. So you want to express that in a whole number that you can easily read. So you would have parts per million, parts per billion. Another weird sort of concentration that's given a lot, and you find this in hospitals particularly, are mass to volume percent. Like, what does that mean? Well, the mass of whatever you're interested in, and in the hospital would be things like salt for like saline solutions, or glucose, or KCl, things like that, it's really essential to have a certain concentration of salts and glucose when you're putting them into your bloodstream. So they want to be able to measure a mass in terms of how much solution there is. And generally we have a mass per mil, and we call that a mass volume percent. That would be like milligrams per mil or percent per mil. And then finally, so volume percent, that's just like if the solute is a liquid, then sometimes it's easier just to put, I took like ethanol, for instance, generally is given in percent. If you buy a bottle of vodka, it says it's 40% by volume, or 80 proof. Proof is basically a 2-to-1 ratio of volume to volume, and then to proof. So absolute 100% ethanol would be 200 proof. And it's just a volume to volume ratio, because the ethanol is a liquid, the water is a liquid. And so it's much easier when you're just pouring these two things together, just measure the volumes because they're liquids. And then there's molarity, which we're familiar with. And then there's molality, which really only has one particular use. And that use is figuring out how much the boiling points of liquids are elevated, or the freezing points are reduced when you add salt to them. So in other words, when you add, probably when you take salt and put it in water, it raises the boiling point of the water. So instead of the water boiling at 100, if I throw a bunch of salt in there, it raises the boiling point to like 102 or 104 or even like 105. It also is the case that if I take salt and put it in water, it then freezes at a lower temperature. How many people are from like someplace cold, like like me? What do they put on the streets in the winter to melt the ice?
Salt.
Salt. Why do they do that?
I thought they did it before, but I guess.
No, well, what does it do? Why did they put salt on that? Because you see, when you put salt on ice, what happens to it?
Well, what I know, Professor, is the salty water have a higher freezing point. No.
Lower is a lower freezing point.
Yes.
So if it's like -5 outside, and you put salt on the ice, you've now lowered the freezing point of the ice to like -10. And so what does it do? It melts. And so that is why you put salt on the ice, because it lowers the melting point and it melts more quickly. So, and the amount that it lowers the boiling, raises the boiling point, lowers the melting point, is determined by how many moles of salt per kilogram of water. And so for water, it's really, really close to molarity, because you see, you have liters of solution and kilograms of solvent. So if it's a really, really dilute solution, which is like, 99.9% water, those two things are going to be pretty close. But when you have like a really concentrated solution that has a lot of solute and not as much water, the difference in molarity and molality are going to be fairly big. But for dilute concentrations, they're pretty much the same thing. So you may see that going forward when you're dealing with boiling point elevation and freezing point depression. So mass percentage, we sort of dealt with this fairly frequently. So we're usually interested in the mass of the solute, right? Because we have a solution, we're interested in what the solution is. It's salt, it's sugar, it's whatever it is. We can also determine the mass percentage of the solvent as well, just by flipping this around. So if it's like a really concentrated solution, I think on the test there was a question with it had 400 milliliters of solution, but only 325 milliliters of it was water. So the volume of the solution is 400 milliliters, but the volume of the solvent is only 325. So it's important that you separate those two things, because some people were confused by that and thought that the final, because there's 325 mils of water, would be the volume of the solution. But remember, when you throw solute in there, the volume is going to increase, because the water needs to make room for the solute. You're going to be throwing ions in there. The water has to move out of the way to allow those ions to form, and then they're going to form cages around those ions, and it's going to change the volume. So the total volume is both the solute and the solvent. All right. Important to know. If you probably have bleach in your house right now, that's an aqueous solution of something called sodium hypochlorite. Oops, go back. Sodium hypochlorite. Should know what hypochlorite is. Hypo, hyper, ite, remember all that stuff? Now this brand, it's written right here as 7.4% by mass. So that means, what does that mean? So it's 7.4% by mass. So if I had
Professor, do we take into consideration? Oh, sorry, I think.
The 7.5 grams per 100 grams.
Right. Yeah, 100 grams of the whole thing, right? So if I have 100 grams of this solution, 7.4 grams of it will be sodium hypochlorite. So what other piece of information would I need to figure that out? So if I took 100 mils out, would that be 100 grams?
Does it? I thought that was only water that goes from.
That's right. So what other piece of information would I need in order to figure out how many grams of hypochlorite do I have? I need another piece of information. What's the other piece of information I need? Density. That's right, right. Density. I need to know what the density is. So if I have 100 grams of pure water, I know what the mass is because that has the density of 1 gram per mil of volume. I don't know what the density of the bleach is. So you'd have to measure that. And that actually, one of the lab I'm thinking of doing this week will involve that very thing in determining the amount of sugar in a solution. The easiest way, or actually the amount of pretty much anything in a solution. A really simple way of doing it is just figuring out what the density is. And then you can just take the density and then convert that to a concentration. So here's a real simple one. So one of the things that, as I mentioned in the hospital, they're always interested in blood concentrations of salts and sugars. There's like two things they want to monitor. Because if you have a big change in the concentration of sugar or salt, that's indication of some nasty business. So you've got a 5 gram sample of cerebral spinal fluid, and you measure that amount of glucose in it. What's the percent by mass concentration of glucose here? So we would just give the concentration just in terms of percent. What would be my answer? Okay, who's gonna get it? Anyone at all? Check in the chat. Close, Aaron. I see a sig fig problem with your answer. There you go. Yeah, it's just convert that to grams. So 0.0375 grams. 0.00375 grams. My bad. Divided by 5 grams times 100. 0.075. Now, if you just have percent, it's assumed that you mean mass to mass. So if you don't have it there, then you have to include what units we're dealing with. And I'll show you what I mean. Like for instance, here we have a concentrated aqueous solution. If you just have, percent, it's assumed you mean grams of HCl over grams of solution. So here you can go ahead and work this out. I will give you the answer. So if you want to check your answer, it's 221 grams if you want to work that one out. Okay. So see if we can get to the end of the chapter. So if it's a volume percentage, generally what you will do is at the end of this, like if you, in your bathroom now, you probably have like rubbing alcohol, like isopropyl alcohol. And basically, usually that is given in volume to volume, because isopropyl alcohol is a liquid, water is a liquid. The easiest way to measure the amount of each one of those things is by measuring its volume. So if it's 10% V to V, that means that it's 10 mils of solute in 100 mils of solution. So 10% of the volume is a specific thing. I think the example that's given here, yeah, it's also isopropanol. It's usually given as a 70% by volume, and I've seen sometimes it's 80%, but it's usually around 60 to 80% by volume aqueous solution. So for these sorts of questions, you need to know densities. So in order to figure this out, you need to know what the density is of the isopropanol. You need to know what the density of the solution is. So the density of that particular solution is 0.785 grams per mil. So if I have a 355 mil bottle, what would be my amount of isopropanol in grams? How would you work that one out? One of the few times you will not have to convert milliliters back to liters. So how many grams is that going to be?
Is isopropanol and isopropyl the same?
Sorry, isopropanol and what else?
And isopropyl.
Isopropyl. I don't know what isopropyl is.
I may be pronouncing it wrong, but it says rubbing alcohol, isopropanol, and the other one.
I don't know what I haven't heard of that. If you could spell it and put it in the chat, I'll find out for you. Oh, isopropanol and isopropyl alcohol is the same thing. Yeah.
Okay, thank you.
Yeah. This is just two different ways of saying the same thing. $200 grams. Check your significant digits, Ryan. How many significant digits? Yeah, 70% does have one, but my density and the volume of the bottle both have 3 significant digits. That's the important thing. Yep, 195. Yeah, so all you need to do here, 1 mil times 355 mils. Just get rid of my mils. And yeah, so don't be fooled. Just because there's only 2 significant digits and 70%, that's just a label on a bottle. The actual information that I need to solve the problem has 3 significant digits in here and 3 significant digits there. So my answer should have 3 significant digits as well. 195. So Sometimes we're going to, not often, we're going to use a mass volume percentage. And it has, as I mentioned, you'll see this in hospitals a lot because they deal with concentrations of important small molecules that are there in relatively small concentrations. But it's useful to have a very simple number. And so what they generally use is mass to volume percentages. So for instance, in saline solution, like the first thing that, if you come into the hospital, what they stick in your arm is a saline solution, basically to stabilize the salt concentration in your blood. Make sure it's not too little and you go into shock. So they have a concentration of 0.9% mass to volume NaCl. Saline actually stands in for sodium chloride, saline. And so if it's a 0.9% M to V, basically it means so if volume, percent means out of 100, right? So my volume generally is going to be out of 100 mLs. How many grams? So 0.9% M over V is equal to 0.9 grams over 100 mils. So that's generally what that refers to. And so that will be your concentration, like I said, of salts, glucose, the important things your body regulates the amounts of. So here's a saline bag here. And you can see, I don't know if you can make it out on it, but it says 0.9%. And so these bags are generally made not on site, like companies, say the chemical companies will make these, because it's really, really important that these be sterile. And so you don't want, people like us with our dirty hands diluting these things and then injecting them directly into people's bodies. You want to make sure that these do not have any viruses or bacteria or anything. So they're made under extremely sterile circumstances. And so this is one of the few times you don't have a stock solution and dilute it because that it's so necessary to keep them clean. And then if people are diabetic, it's really, really important to know what the glucose concentration is. Because if the glucose concentration in your blood gets too high, it sends signals all over your body to do all sorts of things. And it sets off a whole cascade of events that are really not good for you, basically. And so you want your normal concentration of glucose in the blood to be around 70 to 100 milligrams per deciliter. Anyone remember what a deciliter is? Oh yeah, he did start barking at the end of class, didn't he? So what's a deciliter? Anyone remember? It's one of those weird metric things we don't really use very often.
1/10 of a liter?
Yeah, it's a tenth of a liter, which is the same thing as 100 mils. Like, but it's one of those, I don't know, in some instances they use 100 milliliters, other terms they use a deciliter, but it's the same thing. It's the same volume. Don't know why. So generally, what you'll have, so if when you take a droplet of blood here, like you prick your finger, put a droplet of blood on the test strip, put it in here, and it'll spit out a 3-digit number. And you want that to be somewhere between 50 to 120. You want it to be in a normal range. And you really want it to be between 70 and 100 because that's what your body typically has. And if it goes too low, you get hypoglycemia, and you can pass out. If it gets too high, you get hyperglycemia, and then you get this huge flood of insulin in your body, and none of it's good. So take care of yourselves. So then parts per million, parts per billion, I sort of mentioned that earlier. These are really, really easy to deal with. These are also mass to mass. Just remember that these are masses. So mass of solute, mass of solution. So just like mass percent, but instead of percent out of 100, we want out of 1,000,000. Or we want out of 1,000,000,000, because sometimes it's really important to know the very, very, very low concentration. Things that are incredibly dangerous, like lead, dioxin, PCBs, things like that are like incredibly dangerous. You need to know that they're present in extremely low concentrations, because even small amounts of it are toxic. So things like lead, for instance, like in Flint, Michigan, was still a problem to this day. You need trace level. So when people talk about trace level, just a trace, what they're generally talking about is either parts per million or parts per billion. So to remember that, I just want you to remember those are mass to mass calculations. All right, so any questions about what we've gone over today before we go? We'll basically start with chapter 7 on Thursday, and then I'll want to get to energetics. So my groups this afternoon, I will be putting on Canvas the recitation we're going to do, mostly about solution chemistry. And at the end, there's a couple of questions about redox reactions that we will get into on Thursday. And remember, if you have issue with exam, you want to talk about the exam, just email me. We'll set up a time. My office hours tomorrow are going to, I'll put out an announcement. They're going to be delayed. Not that a whole lot of people show up, but for those who want to talk about the lecture or exam or whatever else, it'll be delayed tomorrow till 1 in the afternoon. I will post that on Canvas just to leave a reminder. All right. I will see you this afternoon. If not, I will see you on Thursday. All right.